Today's notes are brought to you by Really Cool Architecture, a place where you can really see lots of parallelograms too. Which brings us to parallelograms. We're going to take a look at parallelograms again, so we're calling this Proofs Day 2. Write your title here. Again, our top section is going to be kind of small, about the size of your daily agenda, and it'll be titled What We Know. And then the two major sections are Observations of Parallelograms 3 and an Observations just on squares and rectangles. So let's start with a list of things that we know, and you're going to add what we know about parallelograms. Go ahead and draw this image, and let's go ahead and label it A, B, C, and D. So because of the definition of parallelograms, here's what I know. I know that it has four sides, because the definition of a parallelogram is that it's a quadrilateral. I also know that AB is parallel to CD, and that BC is parallel to AD. And this section all comes from the definition. But from our observations, we had new things to say. I know that side BC is congruent to side AD because opposite sides are congruent, and I also know that AB is congruent to CD because opposite sides are congruent. So I'm going to go ahead and label that. So these sides are congruent and these sides are congruent. Now our last observation had to do with angles, and those were the opposite angles. So I know that angle A is congruent to angle C, and that angle B is congruent to angle D. And we're going to show that by marking that angles B and D are congruent and angle A and C are congruent. So those are the four things that we know about parallelograms. The first two come from our definition, and the last two came from proofs that we did by looking at the parallelogram and its definition. Now we're going to look at the parallelogram one more time, and this time we're going to look at it from a different perspective again. So this time we're going to change the perspective and look at it as two triangles, but it's not the same two triangles that you might think. So let's go ahead and connect A to C, and here's where it gets crazy. Go ahead and connect B to D. Now the two triangles I'm looking at are this triangle and this triangle. Now since I have this middle point here that doesn't have a name, let's go ahead and call that point E. Okay, so now that we know which two triangles we're actually looking at, let's write down some stuff that we know. Okay, now remember, these lines are parallel and these lines are parallel. Now for this particular observation, we're going to look at AB and CD. Now if I look at AB and CD cut by this transversal, I could say that angle 1 and angle 2 are congruent. What kind of angles are those? Well, look at it. Here's my parallel lines, here's my transversal. Angle 1 and 2 are on alternate sides. So angle 1 is congruent to angle 2 because alternate interior angles are congruent. And that makes sense. Now, we're going to look at this from a different perspective now. So I want you to look at the same two parallel lines, AB and CD, but this time I want you to look at BD as the transversal. So now let's suppose that we're looking at angle 3 and angle 4. What kind of angles are those? Here's the transversal. The blue lines are parallel. Angle 3 and 4 are also alternate interior. So I can say that angle 3 is congruent to angle 4. And why? Well, because alternate interior angles are congruent. Okay, so let's label our diagram. Angle 1 is the same as angle 2. Angle 3 is the same as angle 4. So if this is true, it looks like I could say almost, that those two triangles are congruent. So this is kind of the same position we were in last time. I've just shown that two angles are congruent to two more angles. I've got three options. If I want to prove the triangles are congruent, I could use side, 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 angle, or angle, side, angle. Since I have two angles, I must be looking for angle, side, angle. So I'm missing the side that's included. That would be AB and CD. Now hold on, don't you know something about the opposite sides of a parallelogram? Don't you know that opposite sides are congruent? Isn't that what you told me? I feel like you did. So, you're right. I know that BC, excuse me, I wanted my black pen, that BA and CD are congruent because, well, AB is congruent to CD, and I know that because of one of the observations I did, because opposite sides are congruent in a parallelogram. So remember, my goal was to show that those two triangles are congruent, and I can say that now. I can say that triangle ABE is congruent to triangle, okay, ABE, that's going from the single angle to the double angle through this line. ABE, so I'm going to have to start at the single, so CDE. Triangle CDE. Now, if those triangles are congruent, then I know that all 6 of their corresponding parts are congruent too. So that means all 3 of their sides are congruent and all 3 of their angles are congruent. Now, these are sides that aren't labeled yet, but I know that BE is the same as DE. DE. Isn't that true? So BE is the same as ED. And I also know that AE is the same as EC. CE. So AE is congruent to CE. Now, take a look at what that really means. In the big picture, we weren't looking at two triangles. Before we changed our perspective, we were looking at a parallelogram. In a parallelogram, we drew the diagonals. And what do these green lines mean? What happened to these diagonals? Well, it's like this one came in and it cut the other one in half. In fact, it looks like they both cut each other in half. What's the word for that? What's the geometry word for cutting in half? I'm not looking for midpoint. I'm looking for a verb. It's bisect. Great job. So here's what we can conclude. That the diagonals of a parallelogram bisect each other. Great job. So now let's think about diagonals, but let's also think about them in terms of squares and rectangles. Now, when I think about diagonals, it's different with a square and a rectangle because of the actual shapes. So I want you to think about, what do you know about a square and what do you know about a rectangle? And what do squares and rectangles have in common? And while you're thinking about that, let's go ahead and start by changing our perspective. So the first thing I want you to do is I want you to think about the triangles that make up a square and a rectangle. Okay, so let's actually draw those. So you should have already drawn a square and a rectangle. And now I want you to go ahead and kind of draw these two triangles in here. So maybe draw the two triangles that would make up a rectangle and a square. Okay? And now I want you to really answer that question. What is it? I know what makes a square special and I know what makes a rectangle special, but what is it that these two shapes have in common? And I'm really crossing my fingers and hoping that what popped into your brain was that these have right angles all around. Now, the triangles that would make up a square and a rectangle would mean that if I broke these up, it would make two right triangles. So I want you to write on here that it makes right triangles so that you remember that, because that's what makes this really special. Then let's make a list of things that we know. Now, right triangles are pretty special. The first thing I want you to remember, oh gosh, I really hope you remember this, is the Pythagorean theorem. So take a moment to write this down. So the Pythagorean theorem says that in a right triangle, the sides have a relationship, that the legs squared added together equal the hypotenuse squared. So we're just going to do kind of an experiment looking at a square and a rectangle. So we're just going to do two examples, and I'm going to go ahead and move my key idea down a little bit so we have space for that. So let's do example 1, and let's assume that I've taken that red triangle, this one down here, and there's the right angle, and that its measurements were actually 2 inches and 2 inches, and I'll go ahead and put the inches mark there. Okay, and let's also assume that we have this rectangle too, this triangle. So I'm going to cut my square a little differently. And if I cut this triangle this way, that would mean, let's see, this top part would be 2 inches and this part would be 2 inches too. Okay? So the question is can you use the Pythagorean theorem to find this hypotenuse? Well, I mean, I think if you look at this, you can tell A is going to be 2 and B is going to be 2. So I'm going to find the answer either way, whether I'm looking at this triangle or this one. So if I do my math, I get a squared plus b squared equals c squared, or 2 squared plus 2 squared equals c squared, or, let me move my observations down a little bit more, or 4 plus 4 equals c squared, or 8 equals c squared. Now to undo squaring, I would square root, so that means that c equals the square root of 8. Now you can simplify that, but for our purposes, I'm just going to go ahead and put that this is the square root of 8, and this is the square root of 8. Now it's not a perfect number, it's not a whole number, it's a decimal, it's an irrational number, it goes on forever. But what I really want you to see here is that no matter how I cut up this square, this diagonal will be the same as this diagonal. So if I cut it this way and I get the square root of 8, if I were to cut it this way, that black line would be the same as the red line. They would both be the square root of 8. Okay, now before we go any further than that, let's look at an example 2. So I'm going to go ahead and actually move this over just a little so we have some more space. I'm going to move my architecture over. And let's look at example 2 now. So for example 2, I'm going to imagine that I'm looking at my rectangle cut this way and my rectangle cut, oops, not that way, and my rectangle cut the opposite way. So it would look like this. Okay, and in both cases, no matter how I cut it, I would have a right triangle. So we're going to assume that we're just doing an example here, that this is 5 inches and this is 12 inches. And if I cut it the opposite way, the base would still be 12 inches and the height would still be 5 inches. Now if I asked you to find the hypotenuse in both of these triangles, I think we would agree that the math would be the same. If A is 5 and B is 12, that would be 5 squared plus 12 squared equals c squared, or 25 plus 144 equals c squared, or 169 equals c squared. Now when I square root this, I get c equals the square root of 169. Now unlike the square root of 8, I actually know what the square root of 169 is. It happens to be 13. That means the hypotenuse here is 13 and the hypotenuse there is 13. So again, what am I noticing? The diagonal, if it's cut this way, would be 13, and the diagonal, if it was cut this way, would also be 13. What is the key idea? What do we know about squares and rectangles? Here's what we wrote in our last slide. we wrote in green that in parallelograms, the diagonals bisect each other. And that is true. But these aren't just parallelograms, they're special parallelograms. They're squares and rectangles. So I know that squares and rectangles have congruent diagonals. We just showed that right now. So it doesn't matter how you cut it, the diagonals are congruent and they bisect each other. So here's what you know, just to recap. Squares and rectangles have diagonals that cut each other in half, but the diagonals are also congruent.